Okay, hello class. We are doing section 3.3. We're finally going to have a way to figure out how to tell if a direction vector delta x is improving and feasible. But before we do that, we need to review some stuff from Calc 3. So I've got some facts here about the gradient. The gradient is the vector of partial derivatives. So in Calc 3, we usually talk about functions. Z is a function of x or y. And you could compute del z del x, f sub x of x, y, some other notation you might have seen. And you did that in this case, you would do it for del z del x, del z del y, put them in a 2x1 vector or 1x2 row vector. That's your vector of partials. That gives you a direction of steepest ascent locally or descent locally, again on a surface. So let me make a surface. Take my hand, put it in there. So imagine that this washcloth, this towel is the surface. And if I go to some point on this surface, maybe this little point here, and I point in the direction of the gradient, that will point me the steepest direction uphill. And it's local. So it might be that maybe there's a little bit of a valley and I'm at this point here. It would actually point me down. The direction of steepest ascent would be pointing me up this hill here. But that's only a local direction. If I kept going in that direction, I'd come back down the part of the surface here, right? So that's why we say local. And if you want steepest descent, you do the negative gradient, right? And our notation for gradient is this here. The negative gradient gives you the steepest descent at a point. You can compute a gradient at any point on a surface. Those gradients are always perpendicular to the level curves, and they can be used to determine, this is the last one is the key for us in optimization. These gradients can be used to determine if a direction vector is improving. And we're going to do that with a few more facts here. So notation, if we're in n-dimensional space and we compute a gradient with respect to xi, we have del f del xi. That is an approximate change in our objective function. So in our towel surface, that's a height in z. How much does z change for 1 unit increase in either x or y, x1 or x2? Right? So we're going to change one of those variables just by 1 unit, and we wonder how much approximate change we have. So why is that an approximate change? Pause the video, take a moment to think back to your Calc 3. Why do we have to say approximate? Why is it not exact here? Okay, the answer is because the gradient is related to the tangent plane, and it's going to give us a local linear approximation to the surface. We can actually think about this surface as made up of a bunch of tiny little, there's a quilted surface and there's a bunch of tiny little sections that are flat planes that actually make a geometric approximation to the smooth nonlinear surface. So it's a local linear approximation. And maybe I'll see if I can find some pictures to show you guys a few of these facts. So pause for a moment. Okay, here's a few ideas from calculus material. Zoom in a bit. Okay, so here is a surface. Z is a function of x and y. It's y squared minus x squared plus 1. It is a saddle surface. Maybe you recognize that. Maybe use the tech tool and plot it. Here to plot it, I think with Grapher or CalPlot 3D. So we have a section of the saddle surface. We're interested in the gradient at the point 1, 2. So you take a partial with respect to x, it's negative 2x. With respect to y, it's 2y. Evaluate that at the point 1, 2, and we would get this vector negative 2, 4. So we go to the point 1, 2 in the xy plane, or 1, 2, 4, plugging in 1 for x, 2 for y, we get z is 4. So we're on the surface right here. The gradient actually points us in the direction negative 2 in the x, so we back up a little bit, positive 4 in the y, And so we actually get this vector, black vector shown. That's the gradient from the point 1, 2. If I'm on a different point on the surface though, if I'm over here, we can visually approximate the gradient's going to point up in this direction because it's direction of steepest ascent. Okay, let me show you a couple other pages here. This is the contour map for that same saddle surface. The level curves are labeled z equals 4.2, z equals 7.4, and so on. At this point, the direction I think I'm showing steepest descent here. So this is going in a decreasing minimization direction. So I go from a level curve of around 9 here. I'm pointing down towards the level curve of 7.4. So this is the direction of descent. So I'm actually pointing in the direction of the negative gradient. Get to another point, I reevaluate, do another gradient. And so this is just a path of steepest descent, descending on some part of that saddle, down the side, and we can keep on going. But at each point, we're computing a gradient. Here, 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 here. Okay, next thing. You can compute a gradient at many points, infinitely many points in your domain. Here's a x squared plus y squared, a circular paraboloid facing up from the origin. Here's its contour map. Here's a plot, maybe zoom in a little bit more, of its gradients at every point on this grid. So this little blue line and the length of the gradient actually tells you how steeply you're moving. So this is showing us a positive gradient, the direction of steepest ascent at the point negative, looks like 1/2 here. Here's another gradient at the point 1/2. Here's a gradient at the point 1/1/2. Here's a gradient at the point 1/1. Those are all vectors on the surface and will make sense. We're pointing out and away. When you put the contour map and the vectors, the gradient vectors together, you can see that every one of those blue vectors is perpendicular to the level curve that it actually passes through or touches. And that has to be the case. And many more functions and gradient fields in their gradient vector fields with the contour map. And again, always the blue ones will be perpendicular to the bed. That has to happen, has to be the case, no matter what surface. Okay. Okay, a few more pictures. The point about the approximate change, again, a tangent plane. Gradients are actually how you build your tangent planes. You take the partial with respect to x, partial with respect to y, those together make a plane, and that approximates the surface. So at this hemisphere, if I stop on the point over here on the backside, approximate with a tangent plane, that is a good local approximation that as the plane extends this way, becomes a worse and worse approximation. But you can actually think of any nonlinear surface as built up of a bunch of little tangent planes. And so again, on this surface, I stop and draw a tangent plane. It is a good approximation. There's a little one on the backside of that picture. We have another picture with a tangent plane at the top. We were interested in finding those because there are critical points before extrema in Calc 3. A few more extrema on this one, tangent planes. Again, they are just local approximations. All of these things are local approximations. Okay, so that's all review. And now we're gonna start applying this to our ideas for optimization. So the change in the objective function, if I'm at a point xt in n-dimensional space, again, if you like to think visually, think back to 3-dimensional space. I'm at some point, I want to go to another point, but I want to make sure that it's an improving direction, that the direction that gets me from xt to t+1, this direction delta x, has to be improving. We can get information from that related to the gradient. Here's how. Think about how much you would change. Well, you'd say, how much did I change in each variable? In the x1 and the x2. And then that gives us how much we change in z for x1. But I say, well, how much did I go in that direction? And what was the change vectors component? How much did I do it and how far? And then you do that for the x2 as well. You sum those. But really in doing that summation, hopefully you remember that This is a vector, this is a vector, so we'll think of them as column vectors, these two column vectors. When you do a dot product in your linear algebra or your calculus class, it's the first two components plus the next two, and so on. So that's actually what the sum is doing. So a more compact way of writing that is that we are doing a dot product of the gradient with the change vector. And then we have the scalar lambda. But lambda is positive. So really all we have to look at, here's the key, it boils down to this statement. Delta x is improving if this happens. If you dot your gradient and your direction vector and they're greater than 0, you have a direction of improvement. Now, why does that make sense? Again, this is reviewing some stuff from calculus. Let's say the gradient is this vector pointing in this direction. Let's say the change vector delta x is this one. If you do a dot product and it's positive, it means they're pointing mostly in the same direction. If your dot product is exactly 0, it means they're perpendicular or orthogonal. When we get into higher dimensional space, we usually use that language. And if they are negative, they're pointing in generally opposite directions. If they're complete large negatives, they're pointing more, right? So large positives are pointing more and more in the same general direction. 0, if the dot product between the two is 0, and negative and more negative. Right, so hopefully you remember that from your calculus. Otherwise, check out your cosine formula, the cosine angle formula between two vectors in n-dimensional space. Okay, but of course this would hold if we're maximizing, right? So we need to make sure we put that caveat. This is for maximization. Again, maximization. What do you think happens for a minimization problem? We can say the same thing for minimization. If this is less than 0, then you are improving. If it equals 0, we need more information. Not sure. Okay, let's take a look at this question. Could the gradient itself be a direction vector? That's saying, could you set your delta x to be the gradient for a maximization problem? Would that be a good idea? We know, and here's the proof that it's improving, right? The gradient dotted with the direction vector. So we're going to set delta x to be the gradient. So we're really dotting the gradient with itself. And when you're doing that, you're really doing a sum of a bunch of partials, and that they're going to end up being squared because you're doing it with itself. Squaring a bunch of things, summing them has to be greater than 0. So we know that's a good idea. That's an improving direction. So here's the moral. If you need an improving direction, a great one to choose is the gradient for a maximization and the negative gradient for a minimization. Okay, we're going to work a couple examples now and think about, again, he breaks it down for us. So he's going to give us some facts here. This is a baby steps into the problem. For this one, this is number 7E at the end of the chapter. And we are trying to, he's saying maximize this problem, y1 minus 5 squared plus y2 plus 1 squared. So this is a function that we can actually visualize in R3 because we have two independent variables, y1 and y2 affecting a third one. Really, there's like a z that this is our objective function. He's not giving us any constraints, not having us have any information about that. But the question is this direction vector improving? Well, we don't need to know about the current constraints to answer questions about improvement. Remember, that has to do with the objective function. So he's given us enough information to do this. And so the question is, if we're at this point and we move in this direction, will that be an improving direction? So how do you answer it? Well, you check by dotting this with the gradient at that point. And is it positive for maximization? Will we be improving? So let's get the gradient. So again, f of y1, y2 is this function here. And the gradient of f at y1, y2. At any point, we need to put that in a vector, put the partial with respect to y1, and then the partial with respect to y2. Taking the derivative with respect to y1, we'll have times the power down of power times the derivative of what's inside. So 2 times y1 minus 5 and 2 times y2 plus 1. So we can say 2y1 minus 10, 2y2 plus 2. And they're asking us though about a specific point. So we're at the point 2, 3 on this surface. And let's see, can you still fit it in? Gradient of f at the point 2, 3 then. We plug in 2 for y1 and we'll have minus 6. And 3 for y2 and we'll have 8. So now we are on this surface. Oh, well, let's maybe think about the geometry. Does anybody recognize what kind of surface this is? Circular paraboloid opening up from the point 5 minus 1, opening upwards. So something like this. And we're at this point on the surface, 2, 3. And we go in the direction of the gradient, that's the steepest ascent up the side of that. If we go in the direction -6, 8, we'll be ascending fastest locally. Okay, then to figure out the answer to the question, now we've done enough calculations now, we need to dot this with this. So the gradient of f dotted with the direction vector is going to be -6, 8, dotted with -1, 2. And that is +6 plus 16, right? +6, 16, so 20 something is greater than 0, improving. So let's see what happens on our surface. Let's take a look. Right, so in CalcPlot 3D, I entered the surface. Remember your y1 is going to take x, because that's what CalcPlot 3 needs, is the x and y. y2 becomes y. So I've got the surface in there, -5 plus 1. A circular paraboloid, again, opening up. Let's maybe use the arrow keys to rotate this around to the usual orientation with x and y. So we are at x equals 5, y equals -1. That is our vertex here, and then we're opening up. And now the point of interest is the point 2, 3. And let's see. Yeah, so the point 2, 3 on the surface, x is 2, y is 3. We'd be way up here on the surface. Let me see if I can back out and add a point. That'll help us. 2, 3. What is the z value at 2, 3? We plug in 2, so we'll have -3 squared is 9 plus 16, 25. So I think the z value would be 25. And so we're up on the surface. Let's see if we can find that. Not high enough. Move out a bit more. Oh, here's our point right there. And then we say go in the direction of -6 along the x and +8 along the y. And so that would be a vector like this. And that is a direction of improvement. It's easy to see that. One last thing, let's go back to the surface. This little icon here does the contour plots. Maybe we'll make them step size of 2. And let's get a bunch of them, maybe 20 contour lines in there. Create the plot. And I just need to change my domain, but it makes sense. These are the slices coming through. Here's the point. If you actually plotted the vector, which, let's see, you can do a vector here. Yeah. Plot a vector from the point 2, 3, 25 in the direction. Oh, actually, we just want to do this on the contour map. So we only need 2 coordinates. So I probably need to change this. Okay, let's forget about that right there. But here is our direction of improvement right there. -6 along the x, +8 along the y, point to that direction, and it is improvement, as you can see from the contours. Okay, all as expected. All right, I'm going to erase the board. Okay, now we're going to handle the second part. So we have a way of determining If we're given a direction vector, we know if it is improving by dotting it, the gradient with that direction vector. If that's greater than 0 for maximization, all good, you're improving. We also have a backup. If you weren't given a direction vector delta x, you could use the gradient, and that will definitely be an improving direction for maximization. For minimization, you would use the negative gradient. Okay, but we want our delta x to satisfy two things, improving and feasible. So now we're going to attack the feasible part. How do we know if a direction vector is feasible? Well, first of all, does it have to do with the objective, or does it have to do with the constraints? Remember, whenever you're asked about feasibility, that means you're going to be focusing on constraints. So let's think about our constraints. We're going to have a couple definitions here. A constraint is said to be active, and some books like to use the language tight or binding as well. If at some point x, it's satisfied as an equality. So there has to be a point where that constraint is satisfied as an equality. Okay, well, some constraints are only equalities. We looked at one the other day. We had something like x1 and x2 and x3 somehow combined and they were equal to 23. Or no, we did the optimization one where the sum of two numbers had to be 23. x1 plus x2 is 23. Well, that's already equality, so it's already active. So then you're really focusing on your inequality constraints. Maybe you had x1 less than or equal to 1. So if at that point x, the x1 component is exactly 1, then at that constraint x1 less or equal to 1 is active. Okay, we'll look at some more examples too. But the key idea here, what does this activeness have to do with determining if your direction vector is feasible? So your direction vector x is feasible at some point x that you're at. If that's the case, we only really need to think about which constraints, which active constraints are violated, right? They're going to direct us or give us direction we can't go in. Okay, so let's see how that is the case. Let's go to figure 311. This is on page 116. Figure 311 on page 116. Here's a feasible region in gray, defined by different constraints that are all labeled, like x2 is less than or equal to 6, here x2 axis, here 6, so it creates this. We want less than or equal, so we're on this side, that's the little arrow here. X1 less than or equal to 9, so we shade this way, and that creates this feasible region. You can tell just by looking at this with not examining every constraint right away, it has to be a set of linear constraints, right? Because this is all bounded by linear things. And then you go and look at each constraint, read the equations. Yes, those are all linear, so that makes sense. That's what checks with our visual. So I have a few questions about these different points. Let's go to the point x3 right here, 0.756. It's this point here. Which constraints are active here? So it's going to be the two that are involved in the intersection. x2 less than or equal to 6. It's satisfied as equality because x2 equals 6 at this point. And then this inequality here, 0.4 x1 plus 0.2 x2 greater than or equal to 1.5. If you plug in x1 equals 0.75, x2 equals 6, you'll see that this inequality is satisfied as an equality. So out of all the constraints, the only two that are active at this point are these two, x2 less than or equal to 6. And so we're going to think about our constraint set as active and inactive. We're going to divide our constraint set and label each constraint as whether it's active or inactive. And that labeling happens at every point you're at. We're going to do that in an algorithm called the simplex algorithm in a bit. Okay, let's take a look at another point. Let's look at x1 down here. x1 is 7, 0. Which constraints are active here? You could try plugging in 7, 0 into this one, no problem. Into this one, no problem. Into this one, they're all satisfied. They're all inactive. They aren't satisfied as equality. So it's easy to forget though. Remember, this happens often. Your simple constraint. There's actually a simple constraint in this problem right here that x2 has to be greater than or equal to 0, right? That's what sends us up in this direction. x2 greater than or equal to 0, no, it's actually satisfied as exactly 0. That's what makes it active. Okay, and that's as opposed to say a point like, so we're looking at these different points that are around the boundary. Let's look at one in the interior, x2, 4, 4. Is there any constraint that would be satisfied as equality? No, in fact, any point on the interior, you're safe. All those, you have no active constraints at an interior point. But here's a question. Must an active constraint form a boundary of a feasible region? Well, you might say yes, looking at this picture, but here's one more constraint. This constraint over here actually is what's called a redundant constraint. We needed it to form the model, but then when we actually look at the feasible region, it's really sort of subsumed by a combination of other constraints. It doesn't even factor into the gray shaded feasible region. And so it turns out that it wouldn't matter. If you picked a point over here anyway, you're not even in the feasible region. So it doesn't really make sense to talk about active or inactive. Okay, and then if you, let's go back to x2 again. If you're at this point, what direction can you move to be feasible? They didn't give us any information about the contour, so we're not asking about improving. We're just looking at this feasible region. Which directions can I move and still be feasible? Remember, you're doing x2 plus some lambda delta x, and we're asking about the delta x. Well, take a look. Delta x can be absolutely anything, because as long as lambda is small enough, I start moving this way, I can move that way until I get to the edge. I can move this way. I can move any way a small amount. And so if you're in the interior, any delta x works. Of course, then you want to satisfy the improving condition, but we know how to do that. What else? How about x1? Let's go back to x1. Which directions can you move and still be feasible? I can move up, over, over, over. I just can't go anything down this way, right? So at active constraints, there's our limitation, a set of directions that we can move. You can move along the edge or towards the interior if you're at x1. Okay, let's stay with the book for a moment. Let's go to box 325, page 118. Couple more pages. Okay, so this box here, 325. This is a key box for us. It looks kind of messy, but we're going to see that it's not that bad. A direction vector delta x is feasible for a linearly constrained optimization model at the solution x, if and only if, so we can go both directions here. This is satisfied, a delta x, so the coefficients on that constraint. A is the coefficients on the constraint. So like aij's, let me give an example here. Okay, so this constraint here, 0.4 x1 plus 0.2 x2 greater than or equal to 0.5. The a is 0.04, 0.2. So you just strip off the coefficients on that constraint and put them in a vector called a. If you dot that vector with your feasible, with your direction vector, it will be feasible if that turns out to be positive for all active greater than or equal to constraints. So if you're a dotted with x greater than or equal to b, if that turns out that dot product is positive, then you're feasible. So you're going to divide your constraints into these three classes. Are you greater than, less than, or equal to? And then you're going to make your condition that you're checking. If a dotted with that is greater than, a dotted with that direction, greater than 0 for greater than, less than for less than, equal to for equal to's. But here's a key. Anytime you have theorems, you want to check the hypotheses. So what are the hypotheses associated with this? There's a key phrase in here that I'm going to make sure you're alerted to. This one here, linearly constrained model. So if our constraints are linear, this works. If we have a constraint that's nonlinear, this is not going to help us find the direction vector. So once again, we see why being an LP makes life easier for us. Okay, so I'm going to erase the board and we'll talk a little bit more about that box, that theorem. Okay, well, let's see if we can prove in the forward direction. And then you can do the backward direction. Take it from there. Okay, so this, we want to say, assume the direction vector is feasible and show that then a delta x is greater than or equal to 0 for greater than, And what we're going to do is we're going to start by assuming without loss of generality. Let's just work on the third case. They all follow the same way. So let's work on the equality case down here. Again, we're going to assume going in the forward direction that this direction vector is feasible. Okay, so without loss of generality, we'll just consider of the three cases, the third one, the equality case. And again, start in the forward direction. So we assume the direction vector is feasible. And we ultimately want to show that the conclusion, which was that A delta X equals 0. Well, the feasibility of X tells us that we know AX plus the next iterate, AX plus lambda delta X has to be B. And then it's just a little bit of algebra from there. The current solution is feasible. So we know that means AX has to be equal to B. That's the definition of feasibility, you satisfy all your constraints. And so given that, that means this equation, AX plus lambda times AX plus delta equals B. So that means if this first part, AX equals B, what's left is A times lambda delta X, or lambda AX equals 0. And therefore, A times delta X equals 0 since lambda is greater than 0. Okay, so that's the forward direction. You can do the backwards direction. How would you start that without loss of generality? Let's say we only want to do the equality case. What would you start by assuming? You start by assuming the conclusion, which was that A delta X equals 0, and you want to ultimately, after some work, show that delta X is feasible. Should follow very easily. Okay, so the next thing I want to do is, well, I'll erase the board and we'll work an example. Okay, here's an example from your end of chapter 3, number 11a, and they give us some constraints. 2 main constraints, 3 simple constraints, and a current solution. And they're saying, what are conditions on a delta W, a direction vector, that it has to satisfy in order to be feasible? So they didn't give us an objective, but that's okay, because we're to answer questions about feasible direction vectors and feasibility, we only need the constraint set, so we're good. Okay, so this is our first use of box 3.5. We have 2 equality constraints and 3 inequality constraints that are greater than. So what we're going to do is say, remember, you pull off the coefficients 2, 0, 3 in the first equation, and you have to say that your delta has 3 components, delta W1, delta W2, delta W3, and because those are equalities, those have to be equal to 0, 0, 0. So we actually get an equation, 2 delta W1 plus 0 W2 plus 3 delta W3 equals 0. That's one equation it has to hold. And then the next one is also equality. So we pull off the coefficients 1, 1, 2. That dotted with the proposed direction vector has 3 components. That also, because it was equality, has to be equal to 0, 0, 0. So we'll have delta W1 plus delta W2 plus 2 delta W3 equals 0. 2 equations, 3 unknowns, but we have a few more conditions. And let's make some space. These now are 3 greater than inequalities. So you can really look at the first one, like W1 greater than or equal to 0 is really W1 plus 0, W2s plus 0, W3s greater than or equal to 0. So you pull off your coefficients, 1, 0, 0, dotted with delta W1, delta W2, delta W3. Because it was greater than, this has to be greater than 0, 0, 0. So really we just get one condition, W1, delta W1 greater than or equal to 0. The same thing would happen when you do it with W2 and W3, so we get to the same place, W2 greater than or equal to 0 and delta W3 greater than or equal to 0. So any direction vector that you're going to choose has to satisfy this. So it's a way for us to check if a given or proposed direction vector is feasible. Again, we have a way, we do have a backup way of getting a delta W using our gradient. If this is a max, we would use the positive gradient. If it's a min, we use the negative gradient. But we will also have algorithms in the future where they're gonna say, hey, this is a good idea, build this, follow this algorithm to build your W, and you wanna check that it actually is feasible. Okay, at the end of this section, here's some proposed suggested homework problems from which quizzes will be taken. Make some space. From 3.3, we want to look at 7A, 8B, 9A, 11C, and 12.